Hey everybody, Mr. Covey here. I'm just filling in because I heard Miss Rupnick's not doing a great job. Miss Rupnick, I have a joke for you.
Great.
What is the hottest place in a room?
I don't know. Where?
It's the corner because it's 90 degrees. You need to go back to PSGH.
Sure do.
All right, good luck in your video.
Thanks.
All right, let's get real. Back to related rates. All right, a plane is flying away from an airport at an altitude of 5 miles. When the plane is 10 miles away from the airport, the distance from the airport to the plane is changing at a rate of 240 miles per hour. What is the speed of the plane? Let's have you guys try this on your own. Go ahead and put me on pause. So let's take a look at what we knew. So yes, I did Google airplane drawing to draw that. So we know that the plane has a height or altitude of 5 miles, right? We know that that's constant, which tells us that dx dt, maybe I should have written this down. We do know that dx dt would be 0 then, because that doesn't change. The distance from the airport is changing, from the plane to the airport is changing at a rate of 240 miles per hour, so that's why that's dz dt. And we want to know what's the speed of the plane. So speed going horizontally, that would be dy dt. So I use my Pythagorean theorem. Also note that in order to know this third side of the right triangle, I did have to use my Pythagorean theorem. It wasn't a Pythagorean triple this time, unless you notice that it's what type of triangle? Mr. Covey would be so proud of you. All right, so take the derivative, simplify, cancel out those 2's. Here I plug in my information. Again, dx dt is 0 because that altitude is constant. All right, we solve. I guess you didn't have to rationalize your denominator. I just did because I can. And why not? So speed of the plane is 160 root 3 miles per hour. Next one. Let A be the area of a circle of radius r that is changing with respect to time, dr dt. If dr dt is constant, think about what that means, is dA dt constant? Okay, so think about this. Put me on pause. Write an answer down. So ultimately my answer is no. If dr dt is constant, is dA dt constant? No. Let's take a look. Well, we know that the area of a circle is A equals pi r squared. The derivative of that is dA dt equals 2 pi r dr dt. Circumference times the rate of change of the radius with respect to time. Interesting. Anyway, even if the derivative of radius is constant, what about r? So here's how I worded my answer. I said no, even if dr dt is constant, dA dt is still dependent on r. So if r changes, so would dA dt. If you worded your answer something similar to that effect, then you would have gotten that right. Next one. A spherical snowball melts in such a way that the instant at which its radius is 20 centimeters, its radius is decreasing at 3 centimeters per minute. Decreasing at 3 centimeters per minute. Think about what that should mean about that number. At what rate is the volume of the ball of snow changing? In case you forgot what the volume of a sphere is, don't forget. It's 4/3 pi r cubed. Maybe you remember that, maybe you didn't. Go ahead, put me on pause. Oopsie daisies. Sometimes this thing is harder to work than you would think. Anyway, all right. So I have my formula for volume for a sphere. It's a snowball. We have our given information. We know that the rate at which the radius is decreasing is 3 centimeters per minute. Notice that it's negative because it's decreasing. And that happens when the radius is 20 centimeters. Then we have our dv dt. That's what we're asked to find. What's the rate of volume? So I find the derivative. I plug in my information. And in my final answer, I said that the volume of the ball of snow, or snowball, that sounds better, is decreasing at 4,800 pi centimeters cubed per minute. Notice that I didn't leave my answer as negative. It doesn't matter as long as I give it a direction. That's what matters. Next one. A thin uniform rod of length y centimeters and a small particle lie on a line separated by a distance of x centimeters. If k is a positive constant and F is measured in newtons, the gravitational force between them is below. Pew. Don't forget k is a constant. If x is increasing at the rate 2 centimeters per minute when x is 15 and y is 5, how fast is F decreasing? So think about what that means. What are we solving for? df dt. All right, let's see what you can do. Go ahead and put me on pause. Perhaps you first looked at this and you felt intimidated because there's lots of words and different variables and then constants and then so much going on. Or perhaps you looked at it and accepted the challenge and felt motivated to conquer it. We shall see. Oops. All right. So, first, just keep in mind I rewrote this just so that way taking the derivative would be easier. I recognize my given information. I know that we're solving for dfdt. I know that the derivative of x with respect to time is 2 centimeters per minute. It says it in the problem. When x is 15 and y is 5. And I also know that dy dt is 0. And you're thinking, what? Didn't say that. But think about what y represents. Y is the length of the rod in centimeters. So think about how that makes sense that would be 0. So I found the derivative. I used my power rule and multiplied by the chain. I just rewrote it so it didn't have this negative exponent. It looks a little prettier. And then I substituted in these values that I had recognized above. Now you might have been thinking, well, what do I plug in for k? But we don't know what k is. K is a constant, some constant. So my answer does have k in it. So final answer, I said F is decreasing at 7k per 9,000 newtons per minute. Not that bad. All right, last one. A train is traveling at 0.8 kilometers per minute along a straight track going east. A camera, which is 0.5 kilometers south of the track, is focused on the train. How fast is the distance from the camera to the train changing when the train is 1 kilometer from the camera? FYI, this is a triangle type of problem. So go ahead, put me on pause, and let's see what you can do. So, unfortunately, I couldn't use my artistic abilities in this problem, so I just wrote train and camera. I just didn't want to show off too much, you know. It's a lot for one day. So, it says that a train is traveling at 0.8 kilometers per minute along a straight track going east. So, it started here, it's going east. It's traveling at 0.8 kilometers per minute, so that's why it's the rate, in this case dx/dt. There's a camera down here, hopefully there's a person with the camera, that's 0.5 kilometers south of the track. So this obviously had to have been the track that the train is on. So the camera is 0.5 kilometers from the track. So that's 0.5 is y in this case. Now, dy dt is 0 because that distance, the camera's not moving. Okay. Staying here, so that distance from the track is constant. Now it says, how fast is the distance from the camera to the train changing? So this would represent that distance when the train is 1 kilometer from the camera. So we are solving for dz dt. Now we set up our Pythagorean theorem. We take the derivative. Now we'll know what to plug in for z, dy dt, y, dx dt, but what about x? Well, Pythagorean theorem, again, this isn't Pythagorean triple. Maybe you could have figured out from a 30, 60, 90 triangle. Does work in this case. Oh my goodness gracious. Oh my goodness. Okay. You're kidding. Sorry guys. This is super annoying for me, and I'm sure it's super annoying for you. So I plug in the information. Simplify, I got dz dt is 2 root 3 over 5. So, final answer. I get the distance between the camera to the train is increasing at 2 root 3 over 5 kilometers per minute. Good job. I also want to add to this, follow the guidelines, take your time, do it right, and, ooh, let's get a cool pen for this. And you always have to believe. Oh, and more importantly, persevere. I could keep doing this all day. It's a cool pen. All right, good job.